Alrighty, so remember that we talked a little bit on Friday about free fall and the acceleration of gravity. Remember that free falling objects are any object. These are notes that I already did, so don't be frantically writing these down because they should already be in your notes. These should be the last notes that you had. Alright, so free falling objects are any object that is being acted upon only by the force of gravity. And remember that we said that the force of gravity is an invisible force that pulls objects toward one another. And I told you that everything that has mass has gravity. Everything that has mass has gravity. And the strength of the gravity that is felt depends on how much mass there is and how close these two objects or masses are together. And the two examples that I gave you were the gravity felt when we're standing on Earth, why we're all stuck to the Earth and held down on Earth by gravity is because the mass of the Earth is massive. What a great joke. The mass of the Earth is humongous, right? It's a huge number. It was this number right here. 5.972 times 10 to the 24 kilograms. So that is a massive mass, a huge mass. So therefore, the gravity that we feel because of this huge mass is also huge. We feel a huge amount of gravity, right? But between you and your backpack, you'd say your backpack is 2 kilograms and you're 70 kilograms. That's super tiny compared to the mass of the Earth, right? So we don't feel gravity between our backpack or our bag and our body, but it is there. It does exist. It's just not strong enough to be felt. All right. So this force of gravity that we're talking about is what causes free-falling objects to accelerate as they fall. So the free force of gravity causes free-falling objects to accelerate as they fall. So another way to write that, or another way to think about that, is that as this free-falling object, if we drop something from a 2-story or 5-story building, it's going to be in free fall, right? Because there's no force acting on it. It doesn't have a motor pushing it down towards the ground. It doesn't have something, it doesn't have anything other than the force of gravity causing it to fall, right? And this force of gravity that we just discussed, it causes the object to accelerate as it falls. So that means that it will speed up as it falls. If I drop, let's draw a picture of this, what I'm talking about here. All right, so here we are at the top of this super tall building. Here's the ground down here. This is someone's head with their hair, and they're holding this ball. What they're going to do is drop this ball and allow this ball to free fall. So we can use this thing, it's called a ticker tape diagram. That's what I'm going to draw right now, a ticker tape diagram. So the distance between each of the balls that I'm going to draw here. So let's draw it first actually. Alright, so this ticker tape diagram, this is what I've drawn right here. This is with the ball being separated by increasing increments of space each time. So the ticker tape diagram is what we're going to use to depict the acceleration of a free-falling object. So the space between each of these, this is going to be at some time interval. So they're all going to be the same time interval. Let's say that it's 1 second is kind of a lot. Whatever. For the sake of easiness right now, we'll just say that this is 1 second. So this, let me erase these. This one here, this guy is at time equals 0 before we've dropped the ball. This is at time equals 1 second. This is time equals 2, 3, and so on. Okay? All the way down until we almost hit the ground. So I drew this one purposefully. It doesn't hit the ground yet. but it will hit the ground at 6 seconds. Yeah, it hits the ground at 6 seconds. Okay, make it easy. All right, so this is our ticker tape diagram. If you see this, you can automatically tell that the distance that the ball is traveling each second is not constant, right? So there's an increase between 0 and 1 seconds. The ball goes this far. And I'll draw this differently. It goes this far, right? Between 1 and 2 seconds, the ball travels this far. Between 2 and 3, it travels this far. 3 and 4, it travels this far. So we can see that the distance that the ball is falling with each second is increasing. Therefore, our velocity is increasing because our displacement is changing, and therefore velocity is changing. That means acceleration is, the ball is accelerating, right? It has constant acceleration. That means, let's see here, if I scoot this out, okay. So the constant acceleration due to gravity is going to be 9.8 meters per second squared. Every object that falls, free falls, is going to accelerate at 9.8 meters per second squared. Right? So I'm going to give you two basic characteristics of free-falling objects, and then we're going to come back to this number and do some work with it. All right. So we have two characteristics of free-falling objects that we need to talk about. All right, our two characteristics of free-falling objects. Free-falling objects, first of all, don't experience air resistance. So in order for us to allow all of these things to be true, we have to say that free-falling objects don't experience air resistance. So there's no resistance felt by the object. This isn't necessarily true, but that's what we're going to assume is true for these characteristics and for all the free-falling objects we're talking about. The second characteristic is what I just said to you earlier up here about 9.8 meters per second squared. Free-falling objects have an acceleration of 9.8 meters per second squared downward. And see here I wrote specifically on Earth. Free-falling objects on Earth have an acceleration of 9.8 meters per second squared. We are going to see that there is different, if in places that we have different forces of gravity, for example the moon, we would have a different acceleration due to gravity. It wouldn't be the same as this, and we're going to discuss that further in a couple minutes. But this acceleration, this 9.8 meters per second squared downward on Earth is the acceleration caused by gravity, by the force of gravity of the Earth. All right? So another way, we're going to come back to our picture up here. Another way that we can think about this is at 0 meters per second. We're going to think about our time and our velocity, and therefore how our acceleration changes the velocity or the speed of this object. So time 0, we have a velocity also of 0, right? That makes sense. We're going to do velocity in blue. We can understand that. Velocity also equals 0 meters per second. And if we're not moving, obviously our acceleration is also going to be 0 meters per second squared. Then we move on to 1 second. So, because this is a free-falling object, that means that each second, we're going to put this into words over here, each second, the free-falling objects, acceleration increases. Let's actually say it's velocity. It's velocity or speed increases by 9.8 meters per second. So every second we're going 9.8 meters per second faster. So that means at 1 second, my velocity equals 9.8 meters per second. My acceleration is every second 9.8 meters per second squared. Right here, it's going to be the same. It's going to be increasing each second 9.8 meters per second. Meters per second squared. Same all the way down, okay? You get the picture. All right, so the next second goes by. Now we're at 2 seconds. So because acceleration says we're increasing our speed by 9.8 meters per second, the speed, 9.8 meters per second, every second. So now, if we multiply this, we have to add 9.8 meters onto 9.8 meters here, because we're increasing our speed by 9.8 meters per second, and that will be 19.6 meters per second, because our acceleration says we're adding plus 9.8 meters per second each second. Same thing here, plus 9.8 meters per second. So what will my velocity, how fast will I be going at 3 seconds? My velocity here will be 19.6 plus 9.8 meters per second, because that's what my acceleration is going to give me 29.4 meters per second. Then the next second goes by, I'm going to be traveling plus 9.8 meters per second faster. So my velocity at time 4 is going to be 39.2 meters per second. Now I'm traveling at a speed, a velocity downward of 39.2 meters per second. Acceleration is the same here and at the bottom. All right. Okay, so velocity here, we were at 39.2. We're going to add 9.8 to that, and we're going to get that plus 9.8 meters per second, and we get 49.0 meters per second. Finally, right when the ball hits the ground, what is the speed or velocity? Plus 9.8 meters per second. What is the velocity that the ball is traveling at? It's traveling at a velocity of 58.8 meters per second. All right, so that as the ball hits the ground, it started at 0 meters per second. It sped up every time. Every second, it's speeding up by 9.8 meters per second. So you can think of this also as a car, right? A car starts at 0 and it accelerates 10 kilometers per hour let's say 10 meters per second every second, right? So after 1 second, if it started at 0, now it's going 10 meters per second. After the next second, it's going 10 plus 10, which is 20 meters per second, right? So this is just the concept of acceleration, but we're putting it into, we're applying it to the force of the acceleration caused by gravity, all right? Okie dokie, so we are, of course, going to give this variable here, our acceleration variable, we're going to call it the acceleration due to gravity, or acceleration of gravity. Acceleration due to, I like due to gravity better, so I will probably say that more, but you could also call it, I'm going to erase some stuff here, or at least move this around here. We won't erase it, but okay, you go over here. All right, so we're going to call it the acceleration due to gravity or the acceleration of gravity. It's also the same. Acceleration of. So we're going to be using this a lot, and we're just going to define it as, again, the acceleration for any object moving under the sole influence of gravity. There we go. There's our definition. I think I've already kind of given you that definition, so hopefully, I'm going to leave that actually. Okay, we are going to call acceleration due to gravity little g. It's going to be used in, we're going to use this a lot actually in the upcoming math that we're going to do, and it's equal to the number that I've told you 1,000 times. There we go. Okay. So we're going to take this information and we're going to apply it to the acceleration due to gravity on different places. So this is specifically, I want to make it very clear, this is acceleration of any object under the sole influence of gravity on Earth. So little g is going to change. It will change based on where we are in the universe. G will change based on where we are in the universe. And I'm going to explain that on the next slide. Alright, there we go. So this is all just, I've just rearranged what I wrote on the other page. So you already have all these notes, so don't freak out. Okay, so we're going to talk a bit more about this. Okay, I just told you that it will change based on where we are in the universe. So, for example, we're going to say that G is different on Earth than, let's say, on the moon. This is an example of what I'm talking about. So on the moon, the strength of gravity, or the moon's surface gravity, you could say, the surface gravity, or the strength of gravity, whatever is easier for you to understand, is approximately 1/6 as powerful as the surface gravity of Earth. And if you think about the size of the Earth and the size of the moon, the Earth is real big, right? Earth, let's say that's the Earth. Remember, its mass is humongous, but the size of the moon is very tiny compared, well, not very tiny, but compared to the Earth, it's pretty small. It's actually about 1/6, I think. Let me verify that, actually. I'm not going to say that because I'm actually not 100% sure. It would make sense. Let me look, actually. I am going to look. Yeah, we can't just say that it's 1/6 the size because it actually depends on a lot of other things. So, my bad. We're not going to say that it's 1/6 the size, but the strength of gravity that I feel standing... Whoopsies. Oh, good grief. The strength of the gravity that I feel standing on the Earth is 6 times stronger on Earth than it is on the moon. If I stood on the moon, I would feel 1/6 of the gravity of Earth. So the strength, the gravity on the moon is much less, 1/6 the strength of the gravity felt on Earth, and the reason for that is because the mass of the Earth is much larger. The small mass of the moon, right? Okay, so on the moon, we feel 1/6 the gravity of Earth. So we could write G, because, as I said, remember that G, acceleration due to gravity, is 9.8, but this is only on Earth. So what is acceleration due to gravity, or just G, on the moon then? Well, if I just told you 1/6, right? It's 1/6 the power or the strength of what we feel on Earth. So the acceleration, it's also 1/6 of the acceleration that we feel on Earth. So that means that the that acceleration due to gravity on the moon is going to be 1/6 the acceleration due to gravity on Earth, which means that it is 1.6 meters per second squared is g on the moon. Right? And so that's just one example. I'm going to give you other examples. I'm going to tell you it's going to always be something similar, though. Like the strength of Jupiter is 85 times stronger than the strength of gravity felt on Earth. So what would be the acceleration due to gravity on Earth? So you're going to need to understand. This is just basic, very simple math. You don't need to write the knowns or unknowns or anything for this math problem that I just did. This is just very simple. If I say that something is 1/6 the strength of something, you should know that if you multiply that something by 1/6, you're going to get your answer. Okay, another example. I said that G will be different based on where we are in the universe. G can even be different based on our altitude on Earth. So, I'm going to take my Earth actually, I'm going to copy that and bring it down here. Alright, so, hold on. So, if I'm standing on the surface of the Earth versus standing on the top of, let's say, Mount Everest. Mount Everest, remember, has a very high altitude. It's much higher than sea level. So let's say I'm standing at sea level over here, and then over here I'm standing at, do you remember this? 0.3 atmospheres. Remember when we were taking measurements of altitude in chemistry? So my altitude is, remember at sea level, let's say it's 1 atmosphere. So my altitude is, I'm at a higher altitude, therefore the pressure that I feel is lower. But it's not only pressure that I feel, I also feel less gravity when I'm at this high of, I'm going to erase this, when I'm at this high of an altitude. So at the surface, remember I kept saying surface gravity at sea level is, we'll say at sea level equals 9.8 meters per second squared. The acceleration due to gravity we feel if I drop something relatively close to Earth, right? I mean, like even from the top of the Empire State Building, the altitude is not high enough to change the surface gravity. We're still going to feel about this, but if we go super duper high to, for example, the example I'm always going to use is Mount Everest or Mount something, really tall mountain. Or if I got into an air balloon and I went super high, or if I got into an airplane or a helicopter and went super high. Like that's the kind of altitude I'm talking about, not just like a really tall building. It has to be very, very high. If I go up super duper high to a very high altitude, I'm going to feel less, I feel less surface gravity up here. And the reason that is because gravity is a field. So that means that the closer to the surface you are, the stronger the gravity is. So closer to the surface equals more gravity felt. While when we get further away from the surface of the Earth, we feel less gravity. Less gravity is felt. So when we're a very extreme distance from the Earth, like from the surface of the Earth, like on top of Mount St. Helens, that's in Washington, Mount Everest, we feel less gravity. So when we're this high, would you expect G to be larger than or greater than, figure that one out, greater than or less than greater than or less than 9.8? Well, it's less. It's actually around 9.7 meters per second squared, right? Because we're further away. So you can imagine the surface, like the surface gravity being very strong when you're touching the surface, but the further away you get, the less gravity you feel. So as you get further away from the surface, so here's the surface, we're at 9.8 meters per second. When we're at the top of a mountain, like how we are over here, we're at 9.7 meters per second squared. When we are in an airplane, we're at let's say 9.5 meters per second squared. When we're in a rocket and shooting off and leaving the Earth's atmosphere, maybe we only feel 9.0 meters per second. And then the further and further away we get, here we only feel 7. And if we get all the way over here to the moon, maybe we will feel even less than that. Maybe we'll only feel 4, right? So the further away you get from the Earth, the less gravity you feel, and therefore the less acceleration due to gravity, the less g becomes. G becomes smaller the further away from the surface of the Earth you get, right? Those were made up numbers. The only number that I know for a fact here is I'm ruining Earth here. The only number I know for a fact was this 9.7 and 9.8. So I was making up those other ones as we got further away. But the concept is still the same. So let's look at one more thing. I think we have time for one more little piece of information here. Actually, no. We're going to stop there because tomorrow we're going to be representing free fall by graphs. So what we went over today was acceleration due to gravity. We also talked about how velocity is impacted by acceleration due to gravity, right? And this is going to be the same. I think this is probably the part that was like, oh, what? This is going to be the same no matter what for any object. For any object in free fall, this process is going to be the same. This increase in velocity, it's the only thing that will change for the problems is going to be the time intervals that I give you probably. Yeah. So, if you have any questions about what we've gone over today, you should have gotten all this information from the reading that you did this weekend. And if you have any questions, please let me know. You can start working on your in-class assignment right now. You have way more than enough time to finish that, so you should not have that as homework. So your homework will be to do the reading that is posted on Google Classroom and take notes on that on the next 2 little parts of section 1.6. And yeah, that is all. Please let me know if you have any questions as usual.